radar transmitter produces pulses of microwaves, each with a mean power P, which are emitted uniformly in all directions. A small spherical target of effective area S is placed at a distance d from the transmitter. The target reflects a small fraction k of the energy incident on it uniformly in all directions as shown in the figure below here. Show that the mean intensity IR of the reflected pulse when it is received back at the transmitter is given by this expression. Now the intensity of the wave reaching the target is given by power divided by area, so that is the intensity power per unit area. Now the surface area is given by surface area of the sphere because the wave is emitted in all directions. So we have power received by target will be P over 4 pi d squared, that's intensity, multiplied by the area of the target. The power refracted is a fraction, so it's multiplied by K, and the intensity received back at the transmitter will be reduced by another factor of 4 pi d squared, so we end up with KPS 16 pi squared d to the power of 4. If the mean power is 2 megawatts and the pulse duration is 3 microseconds, calculate the energy in each emitted pulse. So energy in each emitted pulse will be power times time, so there will be 6 joules. Calculate the mean intensity of the emitted pulse at a range 50 kilometers away. So the intensity is power over area, so it's radiating in all directions, so we divide by the surface area of the sphere. So that will give us 6.37 times 10 to the power minus 5 watts per meter square. Calculate the mean intensity of the reflected pulse when received back at the transmitter if the range of 50 km and the product Ks is 1 meter square. So putting into this expression, we get a value of 2.03 times 10 to the power minus 15 watts per meter square. This is a very small number. Briefly discuss the effect on your answer to 3 above if the pulses were emitted in a most parallel beam. Now if the pulses were emitted in most parallel beams, then the energy will not spread out over a large area as it moves away from the transmitter. That means the intensity will not change much as the pulses move away from the transmitter. The net energy reaching the target will be larger than the case of 3 above, and the overall mean intensity of the reflected pulse received back will also be larger.